Hi actuaries! Did you know that you can incorporate your expertise as an actuary to improve your predictive models? Hi, I'm Sam Castillo. I teach actuaries predictive analytics. In this video, you'll see how you can combine Bayesian statistics and credibility theory with the state-of-the-art machine learning method Xgboost. Let's review the basic theory. You have X, which is an estimate of historic overall claims. Let's say that you're in group health insurance. This will be from all of your insurance companies. Maybe you're a consulting firm and you work with a number of different clients, and you just look across all of the clients and find the average claims experience. Y is a more specific estimate for the employer that you happen to be working with. Then you have a credibility factor, which is Z. So you want to be able to predict the risk premium based on both of these numbers. So you could say that this is equal to X times your credibility factor plus Y times 1 minus the credibility factor. And Z is in the range of 0 and 1. So when you have a lot of data and you can really trust your historical experience, then Z becomes smaller, right? So when you have more data from this specific employer, Z becomes smaller, so this just becomes the overall estimate becomes just Y. However, if you don't have a lot of data, then Z is close to 1, and so your overall risk premium is essentially the benchmark that you're working with. So how do we do this in Xgboost? One of the most useful machine learning models is Xgboost. This stands for Extreme Gradient Boosting. This is used by actuaries extensively because of its high predictive power, its flexibility, and its usefulness in a variety of problems, from health insurance to life insurance to automotive claims to pensions, basically any type of data where you are predicting a single outcome using input variables. Xgboost will be very effective. To understand Xgboost, you need to know two concepts. The first is a decision tree, and the second is boosting. So decision trees work by dividing up the feature space into rectangular regions. Let's say that you have two variables, age and BMI. Your goal is to predict whether or not a claim is over $20,000. You divide up everyone based on their age, and you say, for people under age 20, I'll say that they are high cost, and for over age 20, I'll say that they're low cost. You could do the same thing at age 30. You could also ask a follow-up question. For people under age 20, or for people over the age of 20, is their BMI over 15? If yes, you say that those are all small claims, the red circles. So how do you know where the best places to put your cut points? Well, let's look again at age 20. If we create a second partition at BMI 15, we get all of these points in the upper right quadrant to be small claims. Then let's label these R1 for region 1, R2, and R3. If you then look at the decision tree, you can see what the predictions would be for each region. For R1, you at first ask, is age less than 20? And if yes, the predicted probability is 4/5. This is because 4 out of 5 of the points are X's. The same is true for R2 and R3. The second concept to understand is boosting. Boosting is a way of combining results from from multiple models together in an ensemble. This achieves a higher predictive performance than any individual model, while at the same time making the model less prone to overfitting, because each of the models is trained on different subsets of the data. It's less likely for signal to be confused with noise. Boosting works by first making an average prediction of the target. Now, you might say, well, that's a really bad model. Anyone can just predict the average of something, and you'd be right. So it first predicts the average and then subtracts that off of all the values. So then it's actually leaving a residual. Then it tries to make a prediction of that residual. So it takes T1 and predicts T1, and then looks at the residual. So it's like the residual of a residual. And then it keeps doing that. So over time, it corrects for its past mistakes. The boosting prediction is then the sum of all of those. It's a little bit more complicated than this explanation because each of these predictions are weighted in proportion to something called a learning rate as well as the size of the error for that prediction. This means that for observations which have a larger error, the iteration does more to make the correction than for predictions which are already close to the target. So then you fit this model, and here are the results. So on the left here you see the baseline Xgboost model that made no credibility adjustment. This just made a coin flip, 50% or 48%. Compare that to this model where we set the base margin. We said initially it was 90% and 10%. After it looked at the data, it adjusted that to 70% and 49%, which is still much closer to reality. So this is an example of how you could set your initial margin and then only overturn that estimate if you have enough credibility in your data. This is Sam from exampa.net. If you like this video, be sure to hit the like and subscribe button so that you'll be notified as soon as we release additional predictive analytics content.